Okay, here's a problem I didn't assign for homework. This is from Taylor. The problem says, imagine two concentric cylinders centered on the vertical z-axis with radius r plus or minus epsilon, where epsilon is very small. A small frictionless puck of thickness 2 epsilon is inserted between the two cylinders so that it can be considered a point mass and move freely at a fixed distance from the vertical axis. If we use cylindrical polar coordinates, r, rho, phi, and z, for the position, then rho is fixed at rho equals r, while phi and z can vary at will. Write down and solve Newton's second law for the general motion of the puck, including effects of gravity. Describe the puck's motion. Okay, so I'm going to start by trying to draw this, although I admit it's probably not going to be super easy to draw. Let me start with an x and y coordinate system. So x will be coming out towards us, y will be horizontal side to side, and z is straight up. And we're told that there is a cylinder of radius r, and plus or minus epsilon, but I'm going to say like that's actually like the thickness of the line I drew, and there's a puck on this cylinder that is free to move along the cylinder. And we'll say that it has coordinates rho, z, and phi. Okay, so the way I've got it drawn, it's a little bit above the xy plane in the first coordinate of x and y. Okay, write down and solve Newton's second law for the general motion of the puck. All right, well, let's first write down Newton's second law. Newton's second law says that the net force acting on an object should equal mass times acceleration. And what I'm going to do is I'm going to go ahead and undo. The reason I'm making this video is I want to talk about what's expected for your homeworks. So every time we introduce an equation, we want to talk about, where did that equation come from? So this one is pretty straightforward. This is just, we're going to start with Newton's second law. Okay, so next, it says we want to do this in cylindrical coordinates. So I'm going to write this force as F rho hat plus F phi hat plus F z hat, and that should equal the acceleration. And in a previous problem, let's see, so I'm going to go ahead and explain. We're going to apply cylindrical coordinates to F and A, and we're going to use A from homework 0. In homework 0, we found the acceleration of an object written in cylindrical coordinates. Okay, and I actually want to think a little bit about what to put in for the forces. So we are told that there's gravity, so that's going to be a z force. So the force is going to be minus mg z hat. We are also told that that the particle rotates freely along the cylinder. So that means that there's no friction, and so there's not going to be any force along the phi direction. There's not going to be any horizontal forces on this cylinder that point tangent to the cylinder. So we're going to have a force of 0 phi hat, and the force that points inward or outward in the rho direction, it'd be safe to call that a normal force. So I'm going to call this Fn rho hat, and I need to explain all this. So those are my forces. That's going to equal the acceleration, which was rho double dot minus rho phi dot squared r hat plus 2 rho dot phi dot plus rho phi double dot phi hat plus z double dot z hat. Okay. Let's give myself a little bit more room. And let's explain these terms. So this is the normal force from the cylinder. No friction from the cylinder, and gravity. All right, so now apply r dot equals r double dot equals 0. Sorry, rho dot plus rho double dot equals 0 because we're fixed. At rho equals r. Okay, so that gives us Fn rho hat minus mg z hat is equal to, sorry, this was supposed to be rho hat up here, is equal to, all right, rho double dot is 0, so that first term can go to 0, minus rho theta dot squared rho hat plus, and again, I'm looking up here, rho dot is 0, so that first term goes away, so we get rho phi double dot phi hat plus z double dot z hat. Okay, this gives us really 3 differential equations that we can solve. Let me go ahead and put back in plus 0 phi hat. All right, so this gives us 3 differential equations. The radial parts have to be equal to each other, the phi parts have to be equal to each other, and the z parts have to be equal to each other. So the 3 differential equations we get, let's see, the phi parts need to be equal to each other, and the z parts need to be equal to each other. So in black, I have that the normal force has to equal rho phi double dot. So if we find phi double dot, we can find, sorry, that's not right. I took the wrong parts. Equals So the normal force has to equal negative rho phi dot squared. So if we can find phi dot, we can find normal force. The next thing we get is that 0 is equal to r. I'm substituting rho equals r, phi double dot. And then the last differential equation we get is that minus mg is equal to z double dot. Okay, phi double dot is 0. Let's see, so this one can be integrated. So phi double dot is 0. If we integrate both sides, first of all, we can just divide through by r. We get phi double dot is 0. So if I integrate both sides, that tells me that phi dot is a constant, and we should just go ahead and call that omega. So what does that mean? That means that whatever angular velocity the particle started with, it's going to keep that angular velocity. So we can integrate again and get phi is equal to omega t plus phi 0. So this is the motion in the phi direction. And by the way, since phi dot is a constant, we can go ahead and plug in and find that the normal force should be equal to minus r omega squared, and that also is going to be a constant. In the z direction, we can integrate that. And we should recognize this as just constant acceleration. So z dot would equal minus mgt plus some arbitrary constant. If I plug in t is 0, that arbitrary constant becomes vz0, the initial z velocity. Sorry, that's not z double dot, that's z dot. I've integrated z double dot. So if I integrate again, z is going to equal minus 1/2. Sorry, I messed up a long time ago. This was m. No. Ha! There we go. Messed up lots. F equals ma. So this needs mass, and that needs mass. This needs mass, which means this needs mass. Here, the mass canceled with the r, so it didn't really matter. But here, this is important because those are going to cancel. There we go. So this is minus 1/2 gt squared plus vz0 t plus z0, the initial z position. So with gravity, the motion of this object is either going to be just straight down, or it's going to spiral around this thing with constant omega and accelerating z. So if it had a positive initial z velocity, it could start going up and then end up going down. If it had, yeah. So what does the total motion look like? Let's answer that question, because the problem says describe the puck's motion. So let's see. The puck will move constant velocity rho omega along the circumference of the cylinder. At the same time, the vertical motion will be just like free fall parabolic. For example, something like that. Spiraling around the cylinder while falling faster and faster. Okay, my goal here was to show you the kinds of explanations I want so that a reader could follow what's going on. It's good to put in these kinds of explanations to show what the different terms mean. It's good to describe what you're doing. Describe your steps. What is it that you're doing? I don't think so. Here in particular, I said that we used the acceleration from homework 0. It may be more typical that you're using an equation from Taylor, in which case you would say something like, use Taylor 3.7. Okay, but also explain what Taylor 3.7 is for, the acceleration in cylindrical coordinates, or the equation for a rocket with gravity, or whatever that equation is used for. So you need to tell me where the equation came from, but you also need to tell me when the equation is valid, what it's used for. Okay. Hope this helps.